This diagram we're going to use to look at the primary current flow. That's the current flow from the power supply through the coils into the ground. Now that's very critical because this will tell us if all three coils are the same current, same resistance, if all the switches are working properly. We're looking at one of the single traces here on the screen. This is going to help us decide if we have the right amount of time. We want to change our scope trace, slow it down, so we can look at the current flow through several, at least all three of the coils. So what we're going to do is slow our slope trace down a little bit to get at least three patterns on the screen. What we're looking for to see if we have equal current flow in all three of the primaries, through all three of the coils. Here's our slowdown, and we now have 4 patterns on the screen. We need at least 3. We notice they're all the same height. Well, that's critical because this tells us all 3 coils have the same primary resistance. They have the same voltage applied, and they have a good ground. And we know it's a good battery voltage. If the amplitude is right, we know all those things are true. The most critical issue is, are they all, if they're equal, are they the same height? They could be equal with a bad ground. They could be equal with lack of power. But they can't be equal, and they can't be right unless they reach the right amount. What's the right amount? Let's go back to our specs. It says we're looking for 10 amps. We have the 10 amps we're looking for. See how important the specifications are? This will help us identify this. Now let's go back to that diagram and see what we know. We know that all 3 of those coils have the same resistance. Why? Because they had the same current flow. Because we met the 10 amp criteria, we know that the battery voltage applied is normal. Let's say that again. Because they all met the 10 amp criteria, we know that battery voltage is normal. We also know, because they met the 10 amp criteria, that the ground voltage has to be reasonable. We have a reasonably good ground. We've got good power supply from the battery. The charging system's working. The switches are working. The primary current's working. Everything is what it should be. Now, how would we know we should be looking at this in more detail? We can give you another clue going back and looking at our waveforms again. We're going to use our raster pattern of the secondary to judge the current in the spark. We're looking for 1.5 to 2 milliseconds of spark time. 1 is absolute minimum. We need good primary current. Now we had 10 amps of primary current in all 3 coils on this DIS system we were using as an example. We would look for pairs of cylinders that are wrong here, indicating something's wrong with a particular coil. Now if we've done our work with a scope pattern and verified that the wires are good, we've got decent mixture, the reason that's short is the coil is bad. If we've got good secondary, short spark, good primary current, we have a bad coil. This is the shortcut to tying it all together. If we have low current on 2 cylinders here and we find we have low primary current, it's caused by something causing resistance in that primary. Equal current flow on all cylinders, up to spec, we know we should have normal current in secondary. This is tying it all together right here. Now let's go look at fuel pumps and see what we can learn about them. We're going to go back to our specifications again to look at this fuel pump diagram. We're going to use the red area to find that we need to put a jumper in place of the fuel pump relay to measure our current flow. We're expecting about 4 to 6 amps. When we see the pattern on our low amps probe, we see we're running slightly above 5 amps. This means the pump has got good speed and good volume. We can calculate the speed by using the scope to time 1 revolution of the pump. In this case, it turns out to be about 13.4 milliseconds, which is 4,450 RPM. That is good pump speed. Now, if we have a good pattern and good amps, usually we get good volume if everything else is normal, like the fuel filter. Quite often, we have found pumps that cannot deliver the proper amount of fuel to give us a good fuel mixture, and invariably those bad pumps had low amperage. You can use the patterns, but you should have a bad pattern and a low amp failure before you replace a pump. Shops using this technique here have been selling 4 to 5 new fuel pumps or rebuilt fuel pumps every month, as opposed to 1 or 2 per quarter. We're finding more problems with this. It's been around for a while. Use it. It works. This is kind of finishing up the fuel pumps, all the other aspects. Now we've got to go back and see what other factors we've got to look at to keep from having a comeback after we've repaired this vehicle and we think we're done. Is there a possibility of new codes? We're going to try to summarize everything we've done in this long lot of data by looking at a summary. You must start off with a good scan data analysis, which includes checking for service codes. But don't take service codes alone. Look at all the data. When we have service codes other than P300 along with a P300, solve the other codes first, then work on the P300 codes. Sometimes we have things like sensors that go out of range that cause lean mixtures or something else that causes a P300 to set. Once we've determined we have a pure P300 code, then we need to look at the specialized part of our scan data, like we showed you. For the misfire data, we do it in mode 6 and forward, and in scan data for OEM style scan data on GM and Chrysler. It is this misfire data is not available on generic OBD2. You must have a vehicle specific, OEM specific. In our example, we found that this particular case that cylinder number 5 had almost 15,000 misfires. Now we need to go take our secondary ignition to find out why we have this problem. We need to start, we don't know of a faster way, first of all, than using a lab scope. If you have a problem, we start off by finding bad wires. This particular wire is, if you look at the ghost, it's down at 0 volts. This can be a wire or it can be a plug that's carbon tracking. Same thing here, going to 0 volts. Not practical, not real. We have other wires that start off high and have a strong downward slope, and along with double patterns starting at different heights. That's classic example of bad spark plug wires. Here's a ghost on this one that started higher than the previous one. Look for the ghosting, the double image, and the spikes. The high spikes tell us we need to replace them. Now, these spark plug wires are not causing a misfire, but they are going to misfire in the near future. How near? We can't say. That's the point we're making. We're finding everything so we don't get a comeback. Look at these spikes. Make sure you know what you've got. Once we've got the bad plug wires, we need to look for lean fuel mixture. Lean fuel mixture is our #1 cause for misfire codes, along with the bad plug wires. The bad plugs, we have plenty of those, but the mixture seems to be the #1. We've got to divide mixture into all cylinders or some cylinders. 1 or 2 cylinders lean, we go look for a vacuum leak, we look for a bad injector. That's pretty straightforward. The most complicated one, the ones we're into that scare people, are the ones where all cylinders are lean. So we're going to need a special action plan just for all cylinders lean. But let's go look and make sure we understand what it is we're looking at when we talk about this, because we need to go look at our pattern and realize we're not only going to see lean injectors, we're going to see bad wires at the same time, and we can identify both.